So biorhythms are an old notion that we had back in the 60s, that there are 3 cycles influencing your life, driving your life, actually. One has a period of 23 days, one has a period of 28 days, and one has a period of 33 days. And they begin when you're born, and they cycle like this. Everybody born on that same day has the same biorhythm. But this shows that your physical, emotional, and intellectual abilities are all going to peak within the next week. So you've got a good week coming up. Paul, what's your birthday?
June 28th.
Pick a year, any year.
1943.
1943. I shouldn't type in pub. Oh, look at you. Today is the worst day in your life. How did we pick that one? No, 2 days ago was. So, yeah, all right. This is all part of something I call Cleves Laboratory. These are a bunch of MATLAB programs you can download on the web and install them on your machine, and you just get all kinds of fun things here. Oh, this is about, I clicked on that by accident. This is about stiffness in ordinary differential equations. Here's solving the nine body problem for the solar, for the 8 planets and the sun. So we're just integrating Newton's laws here. There's the inner planets. I can turn on a trace and we can see them going around. Look at them from above. Look at them from the side. And then zoom out to see some of the outer planets here. So that's doing the basic Newton's laws of F equals ma and the gravitational law, integrating that set of differential equations. And all the code is here, so this is intended to be something to teach with. Oh, I'm gonna use this in my talk. So let me do it live here, because this is a preamble of the talk. I'm going to show you how you do this in parallel in a minute. But so you're playing blackjack. You're trying to get to 20, close to 21 without going over. You have a jack and a 4. What do you do with the jack and the 4? Well, do you draw on 14? How many people want to draw? How many people want to stay? How many people want to see the dealer's card? The dealer's card is important. That's how you play winning blackjack, is your strategy has to be against the dealer's card. So you have a 14, and the dealer probably has an 18. A third of the cards in the deck are worth 10. So you assume the dealer has an 18, so you're in bad shape here. So you hit, and my God, okay, so it was a lucky day. All right. Okay, you got 18. Dealer's showing a 9. The recommended strategy is in red down here. So we stand, and we lost that one. We got an 8, we hit that. We got 18, stand, we won. Dealer went bust. The important thing is to let the dealer go bust if it's at all possible. 17 against a queen. We're in trouble, so we stand. The dealer went bust. All right, this is good night. We got a soft 18. This is worth a soft 20. This is either worth 10 or 20. We'll say it's worth 20. We'll stand on that and win. Let's play 10,000 hands. Okay, so we're up $940 after 10,000 hands. Oh my God, this is incredible. This is very unusual, all right? This is showing, you can ordinarily win or lose $10, unless you get a blackjack, in which case you win 15, and then you can do things that called double down and split pairs, and that can lead to very important effects on your winning. So I bet you if we play another couple thousand hands, we'll see where. Yeah, that's more like it. See, okay, time to quit. But I'm going to use that in when I give my talk here in a couple of minutes. That was just a warm up. Huh? I should start now. Okay. Oh, let me do that. I got to do this. So this is the double pendulum. If you started out down here, it just sort of swings like a regular pendulum. If you started up at here, it goes chaotic and can wrap clear around. Right? The trick is to try and balance it. Now I have a kind of jitter and a tremor in my hand, so this is actually difficult. All right, it's balanced up there. Right? How long is it going to stay? It's stable, right? Unless you blow on it. All right. Okay, let's get. So that's running MATLAB Live. How many people here use MATLAB? How many people use Python and SciPy? Aha, figured. How many people don't use any of those things? Okay, you just running the big iron, are you? Just all right. So. And now for something completely different. I heard Rick's talk last night. I just listened to the first half of David's talk. This is why I come to these meetings. I enjoy coming to these meetings because I hear about things I never hear about any time. It's important to hear about this stuff, even though I don't think about it on a daily basis. I'm going to go back in history and talk about the origins of MATLAB, clear back even before we had a MathWorks company. And I'm going to tell you about three people that are important in my life: John Todd, George Forsyth, and Jim Wilkinson. At the end of the Second World War, laboratories and universities around the world started to build computers. The National Physical Laboratory outside London, they built, I'm blocking on the name, the codebreaker guy. Turing, sure, what, boy, that's really. Turing proposed building a very complicated machine, but he wasn't allowed to tell them about his secret work during the war, so they didn't think they could build it. They instead built a simplified version called the Pilot Ace. A young mathematician, one of Turing's colleagues, a guy named Jim Wilkinson, built the arithmetic unit, designed and built and soldered the arithmetic unit on this machine, and there he is turning it on at his demo. He went on to become the world's most important, top authority in matrix computation, and he was a friend and mentor of mine and an important figure here at Argonne, as you'll see. Meanwhile, at UCLA, the National Bureau of Standards was sponsoring building the SWAC. They assembled a group of mathematicians into the Institute of Numerical Analysis. George Forsyth is the tall gentleman in the center. Olga Towski-Todd is the only woman in the group, and John Todd, her husband, is looking over her shoulder. 1955, the Institute of Numerical Analysis was dissolved in a political scandal involving battery additives and McCarthyism that I can tell you about later. These scholars all went to universities around the world. Forsyth went to Stanford and the Todds went to Caltech. Here's the math department at Caltech. Olga became the first female professor, a female full professor at Caltech, and Todd is looking over her shoulder. Here's a clipping out of the Deseret News in Salt Lake City, Utah in 1957. They ran stories about precocious high school students. It says, "I'm going away to Caltech. There's electrons orbiting about my head." I got admitted to Caltech because I was from Utah, and that was their idea of diversity back then. I took numerical analysis from Todd. One of the first times such a course was taught any place. We ran on this machine, one of only a handful of computers in Southern California at the time, the Burroughs 205 Datatron. It's a personal computer. Only one person can use it at a time. You had to sign up for a half hour at 2 o'clock in the morning. These cabinets in the back are filled with vacuum tubes before transistors. We wrote our machines in absolute numeric machine language and punched them on paper tape. And I did a project on Hilbert matrices under Todd. Came time to go to graduate school. He said, go to Stanford. That's the only place I applied. Forsyth was a math professor. I went to graduate school in mathematics, but he was in the process of forming what is now the famous Stanford Computer Science Department. We ran on this machine, the PDP-1, DEC's first machine. There's a console here with sense switches on it and a cathode ray display. You could manipulate the sense switches and control the rockets here in the world's first video game. It was programmed by Slug Russell from MIT. It's now in the Computer History Museum in Mountain View. As a graduate student, I went to a meeting in Gatlinburg, Tennessee in 1964. This is the organizing committee for that meeting. How many people have seen this picture before? No, not very many, okay. So this is not the numerical linear algebra group where everybody's seen this thing. This is a famous series of meetings now called the Householder Meetings. I went to one just a few weeks ago, the 20th in Virginia. All 6 of these men had an important influence on my life and on MATLAB. Givens, a second guy here, was the head of the applied math division for a number of years before Messina. This is a page out of my thesis under Forsyth. I used this L-shaped domain to do partial differential equations on. It's now become the MathWorks logo. Here's how our logo has evolved over the years as we've gone from 2D to 3D and added lighting and shading. We're the only company in the world that has a solution to a partial differential equation as the company logo. Forsyth taught this course, numerical analysis, and did matrix computation, wrote some notes. I taught it the next year. I went to Stanford as a graduate student in math, but he started the computer science department, and I ended up being a temporary instructor in the computer science department, taught this course. There's actual software, it became this book. There's actual software in here, programs in Fortran and Algol and PL1 for solving systems of linear equations. Wilkinson came to the US every summer, taught at a short course at University of Michigan, and then came out here to Argonne, as you'll see why in a minute. Here he is in the lecture room at Argonne. He was working on matrix eigenvalue computation, which was then, for dense matrices, was then a research topic. He published his work as Algol programs that were eventually collected in this book. This is still an important reference book. This is the place to go read if you want to see how we do dense eigenvalues today. Don't try to read the Fortran or the C. Read the Algol in this book. It's very readable. But no one could run it because no one had an Algol compiler. And so here at Argonne, the project to convert Wilkinson's Algol to Fortran was called the IcePack project. The first 6 authors here, well, 5 of the first 6 authors were Argonne guys, and I came in the summer. You see Dungara's name on there. You'll be here next week. That was followed by the LINPACK project, which was solving systems linear, software solving linear equation was well known, but not standard. So we had this project to put together a Fortran package to do that. This is a matrix on the front cover. The inverse is on the back. If you run out of things to do, you can try and figure out the inverse while you're waiting here. This is the authors of the LINPACK. That young kid there is Dungara. This is actually his car. Then there's me, Pete Stewart from the University of Maryland, and Jim Bunch from UC San Diego. This picture was taken only a few miles from here at Jim Linus's house, at a party there. It's a LINPACK license plate. Here's the authors 33 years later. Dungara's lost the most hair. I have the neatest shirt. LINPACK is now known as a benchmark rather than a subroutine package, and that's because of this page. This is out of the appendix to the LINPACK manual, where we sent our codes to a couple dozen universities and laboratories and had them run them and time how long it took to solve a system of 100 by 100 linear system. And it took about a second at most of the computer centers around the country, top computer centers. I can't even time it on my machine today because it happened so fast. But back then, that was the benchmark. The machine at the bottom was the machine at Yale. It didn't have enough memory to run 100 by 100. And we had to do 75 by 75 and extrapolate. But Dungara, the numbers penciled in are Dungara figuring out the megaflop rates. Millions of floating point operations per second. And the top machine in the world back then was about 1978, was the machine at NCAR with the brand new Cray machine doing 14 megaflops. That's now become the basis for the top 500, for deciding what's the fastest computer in the world. I don't know if you realize it, but they're still doing the same problem. They're still solving a system simultaneously in the equations. It's a lot bigger. And it takes a lot longer on these machines. Back then, that was representative of scientific computing. It no longer is. This is way off on the edge of what's in LINPACK benchmark, and the top 500 is way out in unrepresentative. It's like the home run derby in baseball. Home run derby doesn't decide who's going to be the best baseball club, but it's still something important to keep track of for historical reasons. I was by the University of New Mexico by this time, and I wanted to have I was teaching linear algebra and numerical analysis. I wanted to have my students access LINPACK and IcePack without writing Fortran programs. So I read this book by Klaus Wirth, who'd invented Pascal. How many people have heard of Pascal? Good, okay. So this has a language called PL0 in here, which is a mini Pascal, and he teaches you how to parse programming language. So I read this book. I wrote the first MATLAB. I wrote it in Fortran using matrix as the only data type. Here's a screenshot from that original MATLAB. There's 80 functions. If you type help, you get 80 functions. That's all there are. There's no M files. There's no toolboxes. You could add functions by getting the Fortran source code from me, which I'd give you, and adding it to the parse table and writing Fortran subroutines to implement it. But that's from the first MATLAB. Here's our joke about how portable machine independent graphics worked in 1979. Early days at Argonne. I give this talk a lot, and the next 3 slides are not, I've added just for tonight, because I want to talk about how important Argonne was. There's a language here called Speakeasy with Stan Cohen in the physics department. And this is Speakeasy. This was before MATLAB. And you see that I learned something from Speakeasy. This is the Tektronix 4081, which Paul arranged to get here. This was a personal computer. Again, only one person could use it at a time. It was the size of a desk. It had only 16K of main memory. But I put MATLAB on this machine by using overlays. And that was an important experience. Here's Wilkinson also would lecture on how to play cricket. And here he is teaching me how to play cricket at a picnic at Argonne, out in the Argonne picnic area. Wonderful environment here in the summers. Thanks, Paul. 1979, I went to Stanford on a sabbatical. I taught the graduate numerical analysis course, 237, and I used the MATLAB you just saw as part of the course. And Bill Grupp was in the class. I've never asked him this before. I remember that the math and the computer science students weren't so impressed because it wasn't research numerical analysis, it wasn't powerful computer science. Trefethen tells me he was impressed. How about were you? It was fun. Okay, fun, fun, right? Just, okay. Yeah, there was more to it than fun, but we'll get to that. Okay, but the engineering students loved it because they were using matrices as their notation in subjects that I didn't know anything about. Control theory and signal processing. I know something about that now, but I didn't back then. And they loved MATLAB. They went off to 2 companies in Palo Alto that had spun off the Stanford EE department. And they got my Fortran from me with my permission. Both of them built commercial software for control design automation. Integrated Systems, Matrix X, was a competitor for MATLAB for years. System Control Technology developed this product with the great name Control-C for doing control. The guy who made up that name and also wrote most of the software is Jack Little. Little was a Stanford electrical engineer. He didn't take my class, but a friend of his did and introduced him to MATLAB. And he threw away all his Fortran and started using MATLAB. In 1983, he came to me and he said he wanted to start a company, make MATLAB commercial. He quit his job at SCT. He bought this computer, a compact portable, disappeared up into the foothills behind Stanford and spent a year rewriting MATLAB in C, actually, which was a gutsy thing because C was brand new at the time. A guy named Steve Bangert had a wife and kids, couldn't quit his job, but he worked on it with Little, and the 3 of us founded MathWorks in California in 1984, and we had a commercial debut at a control conference outside Las Vegas just before Christmas. The first year, MathWorks had 2 to the 0 employees, namely Jack. And next year, Bangert joined him, so they had 2 to the 1 employees. And we doubled every year for the first 7 years. We can't keep that up, otherwise today we'd have 2 to the 33rd employees. And we'd have to hire 2 to the 33rd more this year. Here's a log plot of the size of MathWorks over the last 30 plus years. And we're now up to almost 4,000 employees around the world. Here it is when we had 2 to the 3rd employees. I didn't work for the company for the first 5 years. I was off in another enterprise I'll tell you about in a minute. But I finally joined the company to become the 2 to the 5th employee, actually, the 32nd one on the payroll. The company now has, as I say, 4,000 employees around the world. I've lost track of how many offices we have. We have development offices in England and Scotland and Germany and in India and Bangalore. And then we have sales offices and support offices in a couple of dozen places around the world. But most of the work is done here in Natick, Massachusetts, about a dozen miles west of downtown Boston, just off the Mass Turnpike. And this is our campus. Now, this is an important slide, but I don't have time to talk about it. This is how we make our money. So we're not just doing linear algebra anymore. We're doing all these things: control, embedded systems, hearing aids, image processing, and all of these are important businesses about us. But that's a whole other talk. Instead, I want to tell you a little bit about what, in relation to what you're doing here, and talk about MATLAB and parallel computing or high performance computing. I want to go back again to 1985 and the Intel Purple Silicon Cabinet, it was called. These were single board, this was made out of single board computers. Each board was like an IBM PC, used the same chip as the IBM PC. And you could buy 32 or 64 or 128 boards, get 128 processors. Or you could replace half of those boards with memory boards and get more memory. The first machine went to Yale. And an important part of hardware business is FCS, first customer ship, which when you send the hardware to the customer. We weren't ready to send it to Yale when it was scheduled. Our marketing manager said, if it don't smoke, ship it. But instead, we brought Bill Grupp from Yale. We shipped the customer, not the hardware, first customer ship. And he spent a week or two babysitting the machine in the machine room. MATLAB didn't really work here. You couldn't run it on the parallel computer itself. You could run it onto the front end, which was only a PC. The pipe between the front end and the back end was very slow. And there was no support on the machine back then. We didn't have MPI yet. So message passing was very rudimentary. There was a conference on hypercubes in Knoxville. SIAM published the proceedings, and I show you this is because this is where I first said embarrassingly parallel. So I'm the guy who invented that term. That's my claim. That's the most useful thing that came out. No, that's one of the useful things that came out of this experience. Here's another thing. So the machine required 220 volts. And in the room where we were demonstrating it, we didn't have 220 volts. So we rented this gas-powered generator and ran a cord across the swimming pool into the room. I gave a talk about it, and some guy in the audience made a wisecrack. You know, how many megaflops per gallon are you getting? It was just a joke then. But Key's entire talk was about exactly that. Right? It's not the megaflops per gallon, it's how useful how much fun the software is. Okay. But so, as I say, it was not a commercial success, but we learned a bunch from that machine, and we learned how hard it was to parallelize things if we didn't already know. After that experience and another experience in Silicon Valley, I went to work for my own company in 1989, and we didn't do any parallel computing. We weren't involved in it at all. It wasn't part of our business. The only thing was I wrote a Cleves Corner newsletter article about why there isn't a parallel MATLAB, and this is one of my most widely cited articles. Paul remembers me as being down on parallel computing in general from this, but I wasn't. It was just the wrong thing for MATLAB. We're going to have to distribute. There wasn't enough memory on one node. You'd have to distribute your big matrices across multiple nodes, and that didn't work very well. It's the wrong level of granularity. We needed bigger chunks of work to do, but we didn't have any way of talking about those kind of things. And nobody was buying parallel software anyway, so there was no business in the early years of MathWorks for parallel computing. At supercomputing in 2004, we came out of the closet and realized and announced we were doing parallel MATLAB, and Gates used it in his keynote talk at supercomputing in 2005. Today, that says 2015, this old slide. Today, much of MATLAB is parallel. I'm not talking about high performance computing here. I'm not in the business this meeting is about. We're about high performance computing for everybody else, and or at least parallel computing. So many of the functions in MATLAB are automatically parallelized at a fine granularity. We have two products called the Parallel Computing Toolbox and the Distributed Computing Server, which make it possible for you to do explicit parallelism. This is the stuff that's all kinds of functions throughout MATLAB are using multiple cores and automatically doing parallel processing at that level. The Parallel Computing Toolbox adds these functions to MATLAB to set up a pool of multiple MATLABs to run on your laptop if you've got more than one core, or on your whole cluster if you've got lots of separate machines. And then par4 is a parallel version of the for loop, which I'll show you in a minute. And then there's dozens of other functions for doing explicit parallelism. Now, there is message passing. You can pass messages between MATLAB processes if you feel so inclined. Originally that was done with MPI. I'm not sure if we do it with MPI anymore or do it with Java. Do you know? Yeah. You don't even know about this. This is not on your radar, is it? I'm talking to Grupp up here, so I haven't seen him for a while. Very popular is the GPU array. Take your array from MATLAB, shove it over to the GPU, do GPU stuff on it, and bring it back. Enormously popular. I'm not a big fan of attached array processors. It's the same as I was doing on the Intel machine. I'd have a front-end machine and a back-end machine, shift this stuff back and forth. And David, at one point, David's entire talk was about how to keep all the hardware running, keep those electrons running. At one point, he said, maybe we should think about productivity. But then he swept that aside, right? Now, I'm glad to hear that talk. And Rick's talk last night was all about keeping all the electrons whirling. It wasn't about keeping the people whirling. And that's what we're concerned about here. But we're still doing this kind of thing. So this is an important thing for us. Let me show you a quick demo. Here's the MATLAB program to play 4 hands of blackjack, 4 players sitting at the table. So I took that blackjack program, which I just showed you before you said we were sitting down. That was written long before I worried about parallel. And it doesn't know anything about parallel. But you run 4 copies of it with a par for loop, and then you collect the results. You allocate an array on the front end. You have 4 workers run 4 copies of blackjack and put the results in B, and then you get the results back to the front end and plot them. And here's what you get. So here's 4 different players. Again, it was a winning night slightly. The strategy here is very close to even. So I This is a stand-in for the stock market or investments. The statistics here of this blackjack balance are very, it looks like IBM stock. So, but you run multiple simulations of that with multiple random number seeds, and you can run them all in parallel. And I run it on this machine, and it takes 8 seconds. I turn on parallel pool. I have my 2 cores at work. It takes 4 seconds. That's my speed up, right? That's speed up. Strong scaling here. But here's what's important. Where does B live, right? B lives on the front end, but everybody on the back end puts pieces into B. This is where MPI comes in if we're using it, or maybe we're using Java to do this. I'm not sure anymore, but this is parallel MATLAB would be a lousy way to teach parallel computing because it's all hidden here. There's parallel computing going on, but you don't know how. All right, so MATLAB and quote high performance unquote computing. I can call it HPC in any audience but this. And the distributed arrays, which we invented to do linear algebra, are a useful data structure, but nobody uses them for linear algebra. We now got so much memory on every machine that we are hard-pressed to make up problems that will require more than one memory. So we don't do distributed linear algebra, but we use distributed arrays for this. This is a distributed array. Job managers rule. This is the big concern our guys who are supporting parallel MATLAB have to do. How do you interact with that system software that thinks it's in charge of the machine? And it is. So, and then these are shared facilities. There are dozens or hundreds of people using these giant machines. You're only getting a small piece of the machine. It's not interactive. I wrote MATLAB in the first place in order that I didn't have to go down to the computer center after dinner and pick up my output. And you're still sort of doing this on these machines today. That's important. That's the way these machines are used. But I never use them. I don't want to do any computing like that. My experience was here with a machine at Argonne, Jazz. How many years ago was that? A few? 5 or 6. I came here to run parallel MATLAB on Jazz. If I wanted to interact with it, I got a 10-minute wall clock time with at most 8 processors. I was supposed to debug the thing. I wasn't supposed to actually have any fun with it. So, MATLAB Today is a very complicated product with millions of lines of code. Half of it is in the MATLAB language itself. Another half is in C and Java and Fortran. We're back to Fortran for the linear algebra because we use LAPACK as we get it from Intel with the MKL. MATLAB's historical intellectual basis is in my original business of numerical linear algebra, but its commercial success derives from all those things on that one slide that I didn't have any time to talk about. But I love this. Jim McClellan says the reason MATLAB is so good at doing X is because it wasn't designed to do X. It was designed to do mathematics. So I had no idea MATLAB was going to be used for those things. It's not just a matrix laboratory anymore. Here's some URLs for the information on parallel computing. MATLAB Central is our code repository. That's where you get Cleves Laboratory that I was showing you before dinner. Here's my website where there's a couple of books and my blog. Now, what I do now is I write a blog. Every couple of weeks I come out with a column about something interesting. One came out yesterday, Monday, about using latent semantic indexing, which is low rank approximations to matrices, but matrices derived from doing analysis of text, and it's terms versus documents, and you can discover things about your documents from latent semantic indexing. Anyway, that's in Cleve's Corner blog. Just Google Cleve blog, and you'll get to see it. Okay, thanks a lot. How long did that take, Martin?
No, it's perfect, 6:30. I don't know if you realize the amazing speakers that we are having so far. Any question for Cleve? It's the moment. Don't be shy. Okay, we'll start. So what is the next challenge for MATLAB?
Thank you.
And we didn't coordinate that.
We have dozens of teams of developers, programmers working on all different aspects of MATLAB and using it in all those products I'm talking about. Our big product is Simulink, which is built on top of MATLAB, which I haven't even talked about. But working on Simulink and MATLAB. And what we're trying to do is just move those forward. Everybody has things they want to add to their parts of the products. There's other fields that we have hardly tapped, biomedical stuff, just barely, MATLAB's barely getting in there. And the public domain stuff, the open source stuff, is a big challenge in that community because there isn't anything else established. Who's our main competitor? We don't have one competitor. We have competitors in lots of different businesses. In the mathematics business, Maple and Mathematica are sort of competitors of ours, but they're not competitors in automotive control design automation. That's Bosch and Delphi and so on. So anyway, yeah, David.
At one of the SIAM Math and Industry panels several years ago, you revealed that the number of mathematicians, the number of PhD mathematicians in MATLAB is only on the order of 10 out of those 4,000 employees. Is that still true?
I have no idea. I don't, well, at one time I knew I was the only mathematician at MathWorks. I don't keep track of that. I don't know who has a PhD and who doesn't. I don't know what discipline they're in. So it's a very international crowd. We have people from all over the world. Well, like here, we have people from all over the world who come here and will go to school here, go to school in Boston in particular, and want to stay around, and they come to work for MathWorks. It's a great place to live and work. No, it's not a great place to live. I got out of there. I now live in Prescott, Arizona. That's just moved there. But MathWorks is a great place to work. We just got rated. Forbes rated us number 12 in medium-sized businesses in all disciplines. Paul.
So, Cleve, I remember you saying at one point, maybe 25 years ago, why do we say embarrassingly parallel, even though you coined that? We should say pleasingly parallel. Because there's no science in it, right? You can't do computer science stuff about these multiple independent job screens that only merge towards the end. But, well, embarrassingly parallel, that's much more exciting. I got a lot of kick out of your showing the graph of the number of employees, because I remember one time you and I were talking, I don't know how many years ago, but you said, we're up to 300 employees.
Oh, yeah.
So that was pretty good.
I was living in California, and when the company was just getting started, and I remember going back for the Christmas party and walked in, and they had a supply room with staplers in it and a conference table. You know, it was incredible. Now it's really thrilling to go to a company meeting and to address the company meeting if we can get 4,000 people together for a company meeting. It's very gratifying and totally surprising. Neither Jack or I had any idea this was going to happen. Little is still the CEO. So he went from being the CEO of a one-person company, and he's now the CEO of a 4,000-person company. That's unprecedented. I'm the father of MATLAB, but Little is the father of MathWorks. Yeah. Oh.
What kept you away from joining MATLAB the first 5 years?
Okay, so thank you. First 5 years, half of that was with the Intel parallel computing, with the Intel Hypercube operation in Oregon. And then I went to work for a real Silicon Valley company called Ardent. Anybody ever heard of the Ardent computer? The guys here. Biggest failure in the history of the computer industry up to that time. We had an amazing group. If we'd been a computer engineering department at the university, we would have been one of the top ones in the world. But that's a long story about what happened to Ardent. I learned a lot about Silicon Valley and more parallel computing and graphics going on there. So another important thing.
It was originally called something else.
My goodness, it was originally called Dana. Boy, that's obscure fact. That's because Ben Wegbright lived on Dana Street. But
what's your favorite language to work with when you're not using MATLAB?
I don't know anything else. I wrote my first Fortran program in 1958 and my last one in 1988. So I did Fortran for 30 years. I tried doing it again the other day, 'cause I'm the only guy who knows Fortran at MathWorks. So, and I had something came up trying to hook to some, and I'd forgotten it. My fingers still remember VI, though.
So you and the people that you work with, you started out, at the beginning of the companies, you basically stayed together. What do you how are you guys able to do that? Like, there's always these, feuds in companies that start at a young age, and then I don't know. It's just very interesting to me that you guys are still collaborating and together and working together, and the CEO is the same person who started.
So I suppose we have feuds, but I'm not involved in the day-to-day operations, and as long as I stay out of people's hair, they're okay. One guy sued us for firing him. I know that happened. We've been sued over patents, so we have those kind of things. But it is an amazing. You're right. It's amazingly cohesive and stick together people. So all our management has grown internally. We have two math groups, one for the internal math stuff and one for the external toolboxes. The head of both of those groups are women. So we have, we've been lucky. We've been lucky because the product found uses, found customers. And we've been lucky because we've had good people.
So you mentioned SciPy and with Python. How do you feel about that, and are they a direct competitor to you guys, or?
I thought that was going to be my first question, actually. Yeah, they're serious competitors. So In some way, in some places. So people have a philosophical opposition to paying money for software. Doesn't matter how much it costs. They say MATLAB's too expensive. I say, how expensive is it? They say, I don't know. It's not an economic decision. It's just a philosophical decision. And yeah, so they're important. But our biggest customer is Toyota. Toyota uses Simulink to do production engineering, to design new automobiles. And they're never going to use a unsupported, constantly changing ragtag collection of software like that is. It's fine for people to cut their teeth on, but when they want to get serious, they'll come home. No, it's a serious concern in different fields. In finance, the Wall Street guys will use anything they can get their hands on for their secret. I worked at Los Alamos and had secret clearance there. The guys on Wall Street are even more secret about what they're actually doing with our software. So they buy it. As I say, Biomed stuff buys it. Yeah. Okay, enough about it.
Do you ever wish that maybe MATLAB or MathWorks in general had taken a different path than the one you guys have taken? Like, for instance, maybe you wish you'd stayed the course with parallel computing instead of deviating for 10 or so years?
No, I don't wish that, because there wasn't any course to take, right? I mean, there was no business there. We couldn't have built a parallel MATLAB that made any sense in the beginning. So that was certainly the right decision. What would we have done differently? I just having a heck of a lot of fun. I just got this great job where I'm along for the ride, get to write my blog, and not worry about operating a company. Be interesting to ask Little that. He would never say, though.
Any additional questions?
Okay. Hey. What? Oh. Yeah.
So, how hard is MATLAB pushing into things like deep learning? And I don't know much about where MATLAB is or MathWorks is right now, but
well, we're certainly deep learning like everybody else. We're getting on that bandwagon, and we've been doing neural nets for a long time. Okay. So we know there's been a neural net toolbox since it was possible to write that. We've had global optimization, genetic algorithms. We've had that for a long time. We have a strong statistics group and statistics package. And so we've certainly got the tools for people to investigate that. We have Hadoop. We can do Hadoop on for what that's worth. How do people feel about Hadoop? That's, yeah, enormously important. It was important for us to do Hadoop. It was easy to do, really. There's not much you need to do it. So we have a lot of that stuff. We don't produce a deep learning product per se. We produce the tools you use to study deep learning. I like to non-technical audiences, I compare us compare us to Microsoft Word. Everybody uses Word to write documents, to write novels and newspaper stories and so on. Microsoft doesn't write those things, but they produce the tool for doing that. And we're sort of a Microsoft Word for engineering and science. We're not the ultimate product in any particular discipline, except for maybe control theory. So anyway.
Can I ask,
Yeah.
is there a discipline that you support that kind of surprises you that you would have never expected to support?
I visited, several years ago, I visited Australia, and they took me to see a national accelerator. It was a big atom smasher. They were producing beams of X-rays or something like that. And so this is an enormously complicated machine. We go up to the control room. They've got a graphic user interface to control the machine, and the damn thing was written in MATLAB. That doesn't make any sense at all. All right, but this guy was a physicist. He knew MATLAB. He started using it. He wrote some software, and they started using it not only at the Australian National Synchrotron, but at a couple dozen places around the world. So yeah, what was the name of the thing that just flew past Pluto? What? Yeah. So that's running code generated by MATLAB. So you model the performance of your spacecraft, both its orbit and its control. You're sitting at a computer terminal like all the rest of us, figuring out what this spacecraft is going to do, and then writing a program to control it to get it to do something slightly else. And then pull down on a menu item and generate the code that's going to get sent to the spacecraft. And it damn well better work, right? You don't have a chance to experiment with this thing. So that's amazing. That's being done with our products. Hey, thanks very much. Wonderful questions. I love doing it, and sorry I can't be around for the rest of the week, but I learned some more. Thanks for having me.